Hello everyone, today we are going to talk about increasing and decreasing functions. Now we all know what increasing and decreasing functions are. Basically, a function is increasing on an interval if it gives bigger outputs for bigger inputs. Similarly, a function is decreasing on an interval if it gives smaller outputs for bigger inputs. If we have the graph of a function, then looking at the graph, we can actually see whether it's giving bigger outputs for bigger inputs or whether it's giving smaller outputs for bigger inputs, right? In other words, if we have the graph of a function, then we can actually figure out whether the function is increasing or decreasing on an interval, right? But the problem is, it is hard to get the graph of a function. So we want to find a different criteria that we can actually do something with the function easily, and then from that we can extract the information whether the function is increasing or decreasing on that interval or not. Okay, so we are going to find a criteria to identify when a function is increasing or decreasing on some interval. Okay, so let me start with the definition of increasing and decreasing functions, because we need to define one thing a little bit carefully. So here it is: monotone functions. Okay, so definition: let f be a function then f is said to be increasing on an interval. Let's call this interval I. Let's denote this by I. Okay, so we are not just talking about open intervals. This interval can be closed interval or also can be half open, half closed. Okay, or can be an infinite interval. So I'll just denote that by I. Let f be a function, then f is said to be increasing on an interval I if given any 2 points So let's give those 2 points name x1, x2 in I. Now, as I said, there should be some relation between those two inputs such that x1 is less than x2. Okay, so x1 and x2 are two inputs coming from that particular interval, and x2 is the bigger input. Okay, if that happens, then f of x1 is less or equal to f of x2. Okay, in other words, what does it mean? It means that the bigger input will produce bigger output. Okay, that's what the definition of increasing function on an interval. Okay, similarly, f is decreasing on I if given any 2 points x1, x2 in I such that x1 is less than x2, then f of x1. Now what happens, the function is decreasing, that means it will give smaller output for bigger input, right? So f of x1, since x1 is a smaller input, it will make bigger output, right? Is bigger or equal to f of x2. Okay, so this inequality flips on the output side. All right, now one thing you may notice, why did I write monotone function? So there is one word that actually captures the essence of both increasing and decreasing. What we say is this: f is said to be a monotone function. Some people like to call monotonic function on an interval I if it is either increasing or decreasing on I. Okay, so on I, if it starts to increase, it keeps increasing. If it starts to decrease, it keeps decreasing. If that is the nature of this function f, we say f is monotone on that interval I. Okay, so there should be one other thing that you need to notice, which is kind of an important thing, that we have included here also equality. Okay, equality is included here and also here. Included. Now some people, actually I think Thomas, he does not include that equality. And we have another definition. So this we call a function is increasing if f of x1 is less or equal to f of x2. And if f of x1 is strictly less than f of x2, we say f is strictly increasing on that interval. So we have the notion of strictly increasing and strictly decreasing. Some people don't actually talk about those two things. When they say increasing or decreasing, they just mean strictly increasing and strictly decreasing. Now there is a problem with that definition. I'm going to show you this. Okay, so in this lecture I'm going to prove two propositions. Basically they are very close. I'll prove one for increasing function, and then I'll prove one for strictly increasing function. Okay, and then I will show you something is missing in the strictly increasing part of the proposition, something that we expect will not happen for a strictly increasing proposition. That's why we need to include this equality. This is an important part of this lesson. Okay, and you will see in a minute. All right, so let me give you a graph, and you can tell me, find the intervals on which f is number one is increasing and number two is decreasing. Okay, and the graph is pretty simple. Let's call this A, and the graph looks like this. Let's say. Okay, so let's call this point B. Let's call this C, and this one is D. Okay, now where is this function f increasing? So notice you need to see whether the function makes bigger input to bigger outputs, right? Okay, now if you look at this interval a to b, let's say this is one of your inputs and that is the other one. Okay, now between these two inputs, which one is the bigger one? This one, right? And where is the corresponding output? It is here, right? That means in the y-axis it is there. And where is this output? This is somewhere here, so it is there. Notice definitely the bigger input is making bigger outputs, right? And you can take any 2 points from this interval a to b. Doesn't have to be just this pair of points. Okay, so this function, let's call this function f. This function is definitely increasing on a to b. Okay, is that all? No, it's not, right? Similarly on c to d, it is increasing. You give bigger inputs, it will give bigger outputs. And where is it decreasing? It's here, right? B to C, right? Okay, so from the graph we can say solution f is increasing on A to B union C to D, and decreasing on B to C. Okay? Now if you look at this problem, you will see like you had the graph, and from the graph you could actually determine where it is increasing and decreasing. But the thing is, for most functions we have the formula. We don't know what the graph, how does the graph look, right? It's much harder question to actually graph a function. So we need to figure out some smart way to know when is the function increasing and when is it decreasing. Okay, and that's where we have this powerful derivative criteria for the function to determine whether it's increasing or decreasing. Okay, so now we'll prove proposition 1 that actually gives us that criteria. So proposition 1, let f be a differentiable function on an open interval a to b. Okay, then we have this very important criteria. Number 1, f is increasing on this interval a to b if and only if f prime of x is bigger or equal to 0 for all x in AB. Okay, what does it say? It says that if f is increasing on that interval, then its derivative will be either positive or 0 for every x in that interval. Conversely, if the derivative of f is positive or 0 for every x in that interval, then f is increasing on that particular interval. Okay, and part 2 is just the same version of that for decreasing, and then this sign of this inequality will just flip. Okay, so part 2 is this. F is decreasing on AB if and only if f prime of x is less or equal to 0 for all x in AB. Okay, I'm going to prove just part 1. It's important to know the proof of this proposition, but part 2 is exactly like that. You can do this on your own. So here's the proof. We'll just do part 1. Okay, so first we'll assume f is increasing on AB. Okay, first suppose f is increasing on AB. Okay, and we're going to use the definition of increasing functions on an interval to show that derivative of f is bigger or equal to 0 for all x in AB. Okay, so we need to take a number x from that interval, right? So let x be a number in AB. Okay, and since we are talking about derivative, you know, from the limit definition of derivative, we need to have the difference quotient first, right? So we need some h so that we can calculate f of x plus h minus f of x over h, right? So we need to have some h. Now notice this is my interval a to b, and let's say this is x. Okay, now I will take some value of h so that x plus h is inside this interval. Since h is approaching 0, we can make it as small as we want, so that x plus h is still in that interval. Okay, if h is positive. Also, if h is negative, then x plus h will be on the other side. this is x plus h. So if h is positive, and this is if h is negative, right? Okay, so I'm going to just write this fact that we want our x plus h to be inside this interval a to b, okay? And let h be a number such that x plus h is also in this interval a to b. Okay, now two things will happen based on the sign of h. So case 1, so in case 1 let h be positive. Okay, so h is positive. That means if this is x, then this is x plus h. Right. This much is h, and h is positive. Okay, but what I need to know that x is less than x plus h, right? Then x is less than x plus h. Since h is positive, if you add some positive number, it gets bigger, right? It's that obvious. But now, since f is increasing, f will make bigger inputs into bigger outputs, right? Since f is increasing, on AB, by definition, what will happen? F of x is going to be less or equal to f of x plus h, right? It is increasing, that means it will make bigger inputs to bigger outputs. Okay? Alright, now how does the difference quotient look? It is f of x plus h minus f of x, right? So we'll subtract f of x from both sides. So that means f of x plus h minus f of x is bigger or equal to 0, right? We just need one more thing to get the difference quotient. What is it? We need to divide this thing by h, okay? So we'll divide both sides by h. So 0 over h is just h. And then we have on this side f of x plus h minus f of x over h, okay? What will happen to the inequality? Will it flip? No, because h is positive, right? As long as you are multiplying or dividing by a positive number, inequalities don't flip. So this will remain the same. Okay. Now, one idea from limits, that if you have two functions, one is less than other, and then if you take limits of those two functions, the smaller function will have a smaller limit than the bigger function, right? So we'll take a limit on both sides. And the limit of 0 is 0 because that's a constant function. No matter where h goes, 0 will remain at 0 all the time, right? So this is 0 less or equal to limit h, limit of the difference quotient, f of x plus h minus f of x over h as h approaches 0. But we need to be careful. Our h is positive, right? So in this case, h is approaching 0 from the right side. Okay? Alright, now if you read the statement carefully, what did it mention at the very first sentence? It mentioned that our function f is differentiable at every point on that interval a to b, right? So it is also differentiable at x. So this limit actually exists, and it is equal to f prime of x, right? Since f is differentiable on AB, limit h approaches 0 from the right of f of x plus h minus f of x over h. This guy is just the derivative of f at x. Okay? Now if you just compare these two, what do you get? You get f prime of x is bigger or equal to 0. Okay. Hence, f prime of x is bigger or equal to 0. Okay, so what we did here, we proved the proposition when h is positive. Similarly, we have to finish this proof when h is negative. The proof will be exactly similar, but I'm going to do this anyway. Now case 2, let h be negative. Okay. And then what happens? So x is here. Since h is negative, right? So h should be like this. And so this is x plus h, right? Then x plus h is less than x. H is negative means x plus h, you are subtracting something, right, from x, so it is getting smaller. Just like the previous step, since f is increasing, on this interval a to b, what do we have? Bigger inputs will give bigger outputs. So f of x plus h is less or equal to f of x. Okay, and as we did before, we have to form the difference quotient here. So we'll subtract f of x from both sides and divide by h, and then we'll take limit, and then we'll be done. Okay, so this means f of x plus h minus f of x is less or equal to 0. And here we need to divide both sides by h, right? So we have f of x plus h minus f of x over h, and 0 over h is 0. Okay? But something will happen with the inequality. Yes, it will flip because h is negative, right? If you multiply or divide by a negative number, inequality signs flip. So this is going to be bigger or equal to 0. Okay, now just take the limit h approaches 0. Now since h is negative, h approaches 0 from the left, f of x plus h minus f of x over h, that guy is bigger or equal to 0, but this guy is just f prime of x, that is bigger or equal to 0. Okay, so in both cases we just got the same thing, f prime of x is bigger or equal to 0, and it is happening because my function f is increasing on that interval a to b. Okay, so we have proved half of the implication. Now we need to prove the other direction. And this is the moment where you need to use mean value theorem. Without mean value theorem, there is no luck. Actually, that's why we need to pause our discussion of local extrema. We'll use mean value theorem now, and then from here we can actually jump to the local extrema and finish that story. Okay? So now suppose if prime of x is greater or equal to 0 for all x in AB. Okay? Now let me ask you, what is the definition of increasing function? We took 2 points, x1 and x2 from the interval, right? And x1 was less than x2. Then what did we need to show? We need to show that f of x1 is less or equal to f of x2. That's what we needed to show, right? Okay, so let x1 and x2 be two numbers in AB such that x1 is less than. Now the inequality in the input is strict always. Okay, x1 is less than x2. Okay, now our function f is differentiable on the whole interval a to b, right? And let's say this one is x sub 1, this one is x sub 2. So my function f is differentiable in the whole interval a, b, and differentiability implies continuity, right? So that means my function f is continuous on the closed bounded interval x1 to x2 and is differentiable in the open interval x1 to x2, okay? And those are the two hypotheses of mean value theorem. So the hypotheses of mean value theorem are satisfied. We can immediately go to the conclusion of the mean value theorem, okay? Notice, so that's the next thing. Notice f is continuous on x1 up to x2 and differentiable on this open interval x1 up to x2. Therefore, by the mean value theorem, MVT for short, what is the conclusion of mean value theorem? There should be a number c in between those endpoints, right? There is a number c such that, so that number is coming from the open interval x1 to x2, okay? And what happens? The slope of the tangent at c equals to the slope of the chord, okay? F prime of c equals to f of x2 minus f of x1 over x2 minus x1, right? So that's the conclusion of mean value theorem. Okay, now notice on this interval, no matter what number you plug in, f prime of x is always bigger or equal to 0. In particular, f prime of c is bigger or equal to 0, right? And that will give us the thing we want. Since f prime of c is bigger or equal to 0, we have f of x2 minus f of x1 over x2 minus x1. That thing should also be positive or 0, right? Because this is equal to f prime of c. Okay, now notice x2 minus x1 is positive or negative. That is positive, right? So if we multiply both sides by x2 minus x1, what do you get? We get f of x2 minus f of x1 is greater or equal to 0, since x2 minus x1 is positive, right? Notice x2 is bigger than x1. So x2 minus x1 is positive. Okay, we are almost done. So that means what? I'm now going to add f of x1 on both sides. So that makes f of x2 is bigger or equal to f of x1. Okay? We can just write this in reverse order. So f of x1 is less or equal to f of x2. So what have we proved? If x1 and x2 are two inputs such that x1 is less than x2, then their corresponding outputs have this relation. F of x1 is less or equal to f of x2. That's the definition of increasing function, right? And we're done, okay? So we just need to say one thing carefully. Notice this x1 and x2, they can be any 2 points, right? They are not any 2 fixed points. So no matter which pair of points we pick, we are always going to have this conclusion. Since x1 and x2 were arbitrary, f is increasing on this interval a to b. There you go. So now we have this criteria that if a function is increasing on an interval, open interval, if and only if its derivative is bigger or equal to 0 for every point in that interval. Okay. And for the decreasing part, that was part 2. Similar, you can do it. It's a fun practice. You just have to follow this same thing. You'll have the reverse inequalities. That's it. Okay, now as I mentioned at the beginning, that in our definition we included the possibility that those two outputs can be equal, right? But some people, when they talk about increasing functions, they don't include that equality. Why they exclude that equality, and why did we include that? Okay, so that's the content of the next part of this. Okay, so this is proposition 1. I'm going to do proposition 2, which will be much smaller than this, just a little bit, just few lines, and then we'll do one example. That will be the end. Okay, although I'm going to make a remark, a very important remark at the end. That will take some time, but you don't need to worry about that. Okay, so another definition, let f be a function on an interval. Let's mention the interval letter. Let f be a function, then f is said to be strictly increasing on an interval I if given any 2 points. The difference will be just one little thing. We'll just exclude that equality. Given any 2 points or 2 numbers, x1, x2 in AB, such that x1 is less than x2, right? So what we basically said is we have 2 inputs, one is bigger than other one. Okay. Then f is strictly increasing if the bigger input will make strictly bigger output. Okay. So if this happens, then f of x1 is strictly less than f of x2. So that's the definition. Okay. And similarly, you can define strictly decreasing functions. Similarly, f is said to be strictly decreasing if we have x1 less than x2, then f of x1 is bigger than f of x2. Okay, so a smaller input will make strictly bigger output. So we just excluded the equality from there. This is important, but this has a drawback. We're going to see that. But before we get to that, let me ask you this question. Find the, okay, let f be the function having the following graph. Find the intervals on which, so we'll include all those definitions, okay, on which number 1 f, on which f is number 1 increasing, number 2 decreasing, number 3 strictly increasing, and number 4 is strictly decreasing. So what is the graph? Graph will be very simple. So this one. So this is A, and from A you go like this, go like that. Actually, this should be a horizontal line. Didn't quite look like a horizontal line. Maybe. Okay. Yeah, I'm happy. See, let's just move this a little bit. Okay, so let's call this point D, and so this is E. Okay, almost looks like a car if I extend this side, make some wheels. Anyway, so solution, where is it increasing? Increasing on. So when you say increasing, we include the possibility that the outputs are equal, right? So it should be A to C, right? Increasing on A to C. Okay, so that is number 1. Decreasing on C to E, right? C to E. Okay, and then we have strictly increasing. On where it should be A to B, right? Because here on B to C, notice you give 2 inputs, you know, bigger inputs will have the same output as the smaller input. Okay, so it does not satisfy the definition of a strict strictly increasing or strictly decreasing function. So strictly increasing on what is it? A to B. Okay. All right, and then 4 is strictly decreasing on C to D. Okay. But notice here one thing, on A to C this function is increasing, right? Okay, because if you plug in bigger inputs, the outputs are bigger or equal. But also on D to E, it is the same thing, right? So for example, let's say this is your input, that is your input, those two are your inputs, right? You see the corresponding outputs are same, right? So when we include that equality, we have to actually extend this thing also D to E. Okay, sorry, I didn't notice that at the beginning. And similarly here, see on B to C, if you plug in 2 different inputs, the corresponding outputs are equal, but that's okay with the definition of decreasing, right? So this should be from B to E. Okay, and from this definition you can see like how much we are accustomed with strict increasing and strict decreasing, right? All right, so now the proposition, that's the last proposition. Let f be a function, a differentiable. Okay, let f be a differentiable function, because without differentiability we cannot actually prove this criteria. So we need that differentiable function on an open interval a to b. Now this is the thing. So two things. If prime of x, now this is strictly bigger than 0, okay? If f prime of x is strictly bigger than 0, then f is strictly increasing on the interval a to b. Okay, and there is an analog for decreasing functions. If f prime of x is negative, then f is strictly decreasing on the interval a to b. Just like the previous case, I'm going to prove only part 1. You can prove part 2. It's similar argument, very simple. Okay, so what is the proof? Part 1. Okay. So what do we need to show that a function is strictly increasing? We need any two inputs from that interval, right? Let's call them x1 and x2. So this is x1 and this is x2. Okay. And then what do you need to show? We need to show that f of x1 is strictly less than f of x2. Okay. So let x1 and x2 be two numbers in the interval a to b such that x1 is less than x2. Okay, notice it is the same argument, the mean value theorem argument. Notice f is continuous on the closed bounded interval x1 to x2. Why? Because my function f is differentiable at every point on this interval a to b, and so it is continuous and differentiable, and so in particular it is continuous on that tiny portion inside that, right? And differentiable on x1 up to x2. Okay, hence f satisfies the hypothesis of the mean value theorem, and by that theorem there exists a number c such that c is coming from that open interval x1 to x2, and f prime of c equals to the slope of the chord such that c is between x1 and x2, and f prime of c equals to f of x2 minus f of x1 over x2 minus x1. Okay, but notice f prime of x is always positive, right? Sorry, here's the hypothesis. F prime of x is always positive no matter what x you pick from that interval. Okay, and therefore f prime of c is positive. Okay, but f prime of c is strictly positive, hence this fraction is also strictly positive. And just like the previous case, x2 minus x1, that is a positive number. So if we multiply both sides of the inequality by that, it will not change. So f of x2 minus f of x1 is positive. Why? Since x2 is bigger than x1, right? Okay. But if that is true, then f of x2 is bigger than f of x1. Okay. Which means the same thing as saying f of x1 is less than f of x2. Okay. And now notice x1 and x2, they can be any 2 points from that interval, and therefore f satisfies the definition of strictly increasing function, right? Since x1 and x2 are arbitrary, f is strictly increasing on this interval a to b. Okay, that's the end of the proof. And for decreasing function, you can just follow this proof. You'll be able to do that. Okay, but here's the fun part. I told this before, that the definition of increasing that we are using also allows the possibility of equality, right? And I showed you in the graph. Now, why do some people use equality? Here's the thing. If you look at these two propositions, proposition 1 and 2, you see proposition 1 is an if and only if statement. So it's a two-way road. If my function is increasing, then derivative is positive or 0. If derivative is positive or 0, then also my function is increasing. But if you look at this statement, it says just one part of that implication. It just says that if the derivative is strictly positive, then the function is strictly increasing. It does not say the other part, does it? It does not. Okay? And in fact, that's a very important fact to remember. A function can be strictly increasing even though its derivative is 0. That's an important remark and example. So caution. The converse of proposition 2, that was the last proposition that we proved, is false. Okay, so what it means, i.e. a function is strictly increasing let me write this way, i.e. It is not always true that a strictly increasing function will have a strictly positive derivative at every point. Okay, and what can be an example of that? It's a very common example. So example, so here's the example. Let f of x be x cubed. Okay, and if you look at this function, you'll see it is strictly increasing. It is. Okay. So for example, these two are your inputs. that is on the right side, so that means it is the bigger input, right? And the bigger input will give you bigger output, right? It is here. On the y-axis, if it is on top, it's bigger, right? And then suppose you take these two, and then that is the bigger input and the corresponding output is bigger, right? And so on and so on and so on. Okay? But f prime of x is what? 3x squared, okay? And hence f prime of 0 is what? 3 times 0, which is 0, right? So we cannot actually get the converse of that statement. There are strictly increasing functions, but they don't have their derivative to be strictly positive at every point, okay? And that's the reason why some people use equality in the definition of increasing functions. They like to call increasing functions and strictly increasing functions. But some people just want to remove that equality and call them increasing function. But that can come with some, you know, payoffs. Anyway, so that's a very important and satisfying thing. But notice the most important part here is actually proposition 2. Because we need proposition 2 to find local max and local min. Okay, so why is that? I'm coming to that, but let me just solve a simple example. Okay, so this is about finding intervals on which a function is strictly increasing and strictly decreasing. So example, find the intervals on which the function f of x equals to, say, x to the power 4 minus 8x squared is number 1 is strictly increasing, and number 2 is strictly decreasing. Okay? Notice we are not graphing this function. At the very first problem, what did you do? We graphed a function, and then from that graph we figured out where it's increasing or decreasing, right? And now we are going completely to the world of, you know, algebra, kind of. We just have the formula of that function. We don't know how it looks. So we have to use some tool, and the tool is proposition 2. So what does proposition 2 says? Proposition 2 says that if f prime of x is strictly bigger than 0, then our function f is increasing on that interval. If f prime of x is strictly less than 0 on some interval, then our function is strictly decreasing on that interval. And that's what we are looking for, okay? So solution. So first of all, we need to figure out f prime of x, right? So f prime of x is 4x cubed minus 16x. And we can factor out what? 4x, and that will give us x squared minus 4, right? Okay. Now notice, what are we looking for? Strictly increasing, that is the same thing as solving for f prime of x is bigger than 0. It's just that inequality, and this means this is less than 0, right? So we are looking for x values which makes our derivative either positive or negative, okay? But if you want to solve for those kind of inequalities, what should you first look at? You should look at first the zeros, okay? Now set this equal to 0. Okay. By the way, this is actually finding the critical numbers of the function, okay? In the next lecture I'm going to talk about finding local maximum and minimum, and then I will just call this finding critical numbers. Okay, so if prime of x equal to 0, if you set that equal to 0, then what you get 4x times x square minus 4 equal to 0, and that gives you x equal to what? 0, and here plus or minus 2, right? So negative 2, 0 and positive 2, right? So these are the points where first derivative is 0. So definitely my first derivative cannot be positive or negative on those 3 points, right? Okay, but these 3 points are very influential to get those things. How? Here is the thing. So this is negative 2, 0 and 2, and my first derivative vanishes at those 3 points, right? And now notice my first derivative is also a polynomial, and polynomial functions are continuous, and for continuous functions we have what? Intermediate value theorem, right? And intermediate value theorem says intermediate value theorem says if at one point you have positive, at some other point you have negative, then you must have a 0 in between, right? Okay, but notice these are the only zeros. What it means is on each of these 4 intervals, the derivative function will have exactly one sign. It is either always positive or always negative. It cannot be both, right? Because say on this interval, negative infinity to negative 2, if it were positive at one point, negative at some other point, then since my function is continuous, it definitely hits the x-axis at some point. So we will get 1 more zeros, but that's not possible, right? Because this function has only these 3 zeros. By this function I mean f prime. Okay. All right, so what we do then, we do the interval test. So intervals, so these numbers actually split the whole real line into 4 sub-intervals. So negative infinity to negative 2 is the first one, and then negative 2 to 0 is the second, and then 0 to 2 is the third, and then 2 to infinity is the fourth. All right, and then from each interval I will take a test point. As I said before, it doesn't matter which point you choose. If it is positive at one point, it will give you positive at every point. Okay. So from this interval, what is the easiest that I can choose? Negative 3. Okay. And then this is sign of the test value and sign of f. Okay, so if I plug in negative 3, say 4 times negative 3, that's negative, right? But negative 3 squared is 9, 9 minus 4, that's positive. And negative times positive is negative, right? So this input will make f prime to be negative, and therefore f prime has to be negative everywhere in this interval, right? Sign of f prime, sorry. So on this interval, this is always negative. Okay, now negative 2 to 0, I will plug in what? Negative 1. Okay, 4 times negative 1 is negative, and then negative 1 square minus 4, that's also negative. Now negative times negative is positive, so f prime is positive there, and so it's positive on this whole interval. And then from 0 to 2, I will choose 1, that will make it positive, times 1 minus 4, that's negative. Positive times negative is negative, so f prime is negative on this interval. And finally from 2 to infinity, I will take 3. 4 times 3 is positive, and then 9 minus 4 is 5, which is also positive. Positive times positive is positive, so this is positive. Okay, so what it means is this: the derivative function is positive on this interval negative 2 to 0 and 2 to infinity. And therefore, by proposition 2, since f prime of x is positive on these intervals, our function f is strictly increasing on these 2 intervals. Okay, and since f prime of x is negative on these two intervals by the previous proposition, our function is strictly decreasing on these two intervals. That's the end of this problem. Okay, all right. Therefore f is strictly decreasing on negative 2 to 0 union 2 to infinity, and strictly decreasing on negative infinity to negative 2 union 0 to 2. Okay, actually we can right now we can say where does this function have local maximum and local minimum, but I'm not going to do that, even though I could. Okay, or maybe I should. I don't know. Okay, so let me just explain this picture a little bit. So this is negative 2, this is 0, and this is 2, right? So on this part, my function is decreasing, right? So it goes down. Like this. And from negative 2 to 0, it increases, right? But after 0, it decreases again. Okay, and then at 2, it decreases up to 2, and after 2, it increases again. This is a schematic diagram of this. So notice what happens. It has a local minimum here and a local minimum there, right? And it has a local maximum. Actually, this picture should be a little bit better than this. A local minimum over there, a local maximum over there. So what happens, a function, okay, let me just graph a function. Suppose you have a function like this, okay? A function has a local maximum at a point if on the left of it, it is strictly increasing. Okay, and right after that point, it is strictly decreasing. Okay, and then it has a local minimum at a point if on the left side of this it is strictly decreasing, and after that it is strictly increasing. But this thing means what? F prime of x is strictly positive. This thing means f prime of x is strictly negative, and this means again f prime of x is strictly positive. And what happens at those points here and there? F prime of c and f prime of d are 0 because those are critical numbers, right? And my function is differentiable in this case. So there you go, that's called the first derivative test. First derivative test. Okay, that's why we had to wait for the second part of extrema. But I'm going to solve more problems in next video and finish the story of local extrema. But that's kind of the gist of that. Okay, I want to make one comment before I end. If you're learning calculus for the first time, you may completely ignore this part. You don't need to know. If you know calculus a little bit, then maybe this will be useful for you. Although I don't say it's going to be useful, it may be harmful. Okay, so yeah, some people like to define this thing, say, so this is a remark. some people, or I mean not some people, how should I say this thing? Okay, we can define increasing and decreasing behavior of a function at a point. Okay. So what is the definition? A function is increasing at a point if it is increasing in some interval containing that point. Okay. So roughly this is the idea. A function is increasing also I should make here decreasing in the parentheses. A function is increasing at a point if it is increasing and correspondingly decreasing in some open interval containing that point. Okay. So like this, if this is the graph of a function, okay, it's a horrible x-axis. Let's say this is my point, say CF of C. We'll say this function is increasing at C because there is an interval like this where this function is increasing, and this interval contains the point C. Okay, that's one idea. But the thing is, now like people use this thing, but then there is one problem. It's not a problem, it's just a cautionary remark. So at the beginning we proved one proposition, right? Function is increasing on an interval if and only if its derivative is strictly bigger than bigger than or equal to 0, right? That thing will not happen here anymore. So it can happen that a function has a positive derivative at a point, still it's not increasing. Okay, so once you define things in a new way, once you narrow down possibilities, okay, or you extend the possibilities, you always have to be very careful about the statements you prove. So I just wanted to make this remark, and that will be the end. So that was remark, and this is a caution. Let's make it also an example. Okay. Let's just write caution first. Okay. It can happen that that a function has strictly positive derivative at a point, and yet it is not increasing at that point. Okay, so if you allow this definition of increasing and decreasingness of a function at a given point, then you have to be careful about the proposition. So that proposition will not hold anymore. Once again, I'm saying if you're learning calculus for the first time, you completely ignore this part. Don't worry about this at all. So this is an example about that caution. The example, let f of x be this function. It's x plus x squared sine 1 over x if x is not equal to 0, and it is 0 if x is equal to 0. Okay. Then what is f prime of 0? This is from the limit definition of derivative. This is limit of the difference quotient, limit of f of 0 plus h minus f of 0 over h as h approaches 0, right? But what is f of 0? That is just 0. So this is, and 0 plus h is just h. So f of h over h, right? Okay, so let's now write down what f of h is. So this is limit h approaches 0. So now we are substituting h for x, right? So this is h plus h square sine 1 over h over h. And we can factor out one h from the top and cancel out that h. So this is limit h approaches 0, 1 plus h sine 1 over h. Okay. And you can use the squeeze theorem. Using squeeze theorem, you can show that we can show that limit h goes to 0, h sine 1 over h, that guy is 0. Okay, what you have to do is just need to change the variable. You write 1 over h as say t or u, and then use the squeeze theorem. Then you will get this thing 0. So this limit is 0, and therefore f prime of 0 is just limit of 1 as h approaches 0, which is 1. Okay, hence f prime of 0 equals to 1. Okay, which is strictly positive, right? But is my function, is this function f increasing at 0? No. Okay. But what is f prime of x? Derivative of x is 1, and then x squared sine 1 over x, we have to use product rule there. Derivative of x squared is 2x, so this is 2x sine 1 over x. And then we have what? Derivative of there it is, what is it, sine 1 over x. Derivative of that is cosine 1 over x. And if you use the chain rule, then we get negative 1 over x square. Okay, and you have that x square. Okay, so this is going to be negative cosine 1 over x, right? Oh, yeah, sorry, I need to, I forgot one constant, so I need to put a 2 over here, 2x square. Sorry about that. So this is 2h square. So this is 2h, yeah, this goes to 0, so this is 1, so then this is going to be 4x and 2x squared. Okay, yeah, I mean I'll tell you why I need that too. Okay, so this is now 1 plus 4x sine 1 over x, and this is negative 2 cosine 1 over x. Okay. So that's the derivative, right? Now if a function is increasing in some interval, then what happens? Derivative has to be positive at every point, right? If it is decreasing, then derivative has to be negative at every point, right? But what happens in this case is this interesting fact. So this is the interval, this is 0, and then no matter what interval you choose, you can always get a point, say, like, let's take okay, first suppose x equals to 1 over 2n pi, okay, where n is any integer. Okay, so then notice as you're increasing your n, this number is going to be here, and then gradually as you're plugging bigger and bigger values, these numbers are becoming closer and closer to 0. Okay, so every interval containing 0 will have numbers like this. Okay, then what happens, then f prime of 1 over 2n pi, this guy is going to be 1 plus 4 times 1 over 2n pi times sine 2n pi minus 2 cosine 2n pi, right? But sine 2n pi is 0, so that part will be gone. What is cosine 2n pi? So n equal to 0, right? That is cosine 0, which is 1. N equals to 1, that is cosine 2 pi, that's also 1, right? So cosine 2n pi is always going to be 1. So that means f prime of 1 over 2n pi, that thing is 1 plus 0 minus 2 times 1. Okay, that's why we need that 2, because we want to make this negative. So 1 minus 2, which is negative 1. Okay, so if prime is actually negative at all these points, right? But f prime of 0 is positive, so you don't have the same sign for f prime, so it's not increasing or decreasing, right? And just to check this thing one more way, now suppose x equals to 1 over 2n plus 1 pi. So here we took even multiples of pi at the bottom. Now we are taking odd multiples of pi, where n is any integer. Yeah, then what happens, then f prime of 1 over 2n plus 1 pi, this guy is 1 plus 4 times 1 over 2n plus 1 pi times sine 2n plus 1 pi, okay, and then minus 2 cosine 2n plus 1 pi. Okay, once again sine of any integer times pi is 0, so this is going to be 1 plus 0, negative 2. Now this is interesting. Cosine of 2n plus 1 pi, that is, say for example n equal to 0, right? So that is cosine pi, and cosine pi is negative 1. Cosine, and then take n equals to 1, then this is cosine 3 pi, which is also negative 1. Okay, it's always going to be negative 1. So this is negative 2 times negative 1, so now this is 1 plus 2, and this is 3. Okay, and these numbers are also here. It is. Okay, so what it says is no matter what interval you pick around 0, okay, there will be these numbers like 1 over 2n pi, 1 over 2n plus 1 pi in those intervals, and whenever you plug in those numbers, sometimes like if you plug in this kind of numbers, your derivative will be negative. If you plug in those numbers, your derivative will be positive, okay. Therefore the function is neither increasing nor decreasing. Actually what happens here is it is oscillating so fast, okay. So you see it is increasing, and right after that it's decreasing, and then it's increasing, and then it's decreasing, okay. It does not have any like unique feature, even though the derivative at 0 is positive. So that's the message, okay. So don't apply theorems where they don't apply, where your hypothesis is not satisfied, okay. So the propositions we have are for intervals, not for points. This is a common misconception that people think, okay, if derivative at a point is positive, then derivative in some neighboring points has to be positive and function has to be increasing. No, that's totally wrong, okay. That doesn't happen all the time, okay. It can happen sometimes, but it's not absolutely true, okay. Therefore f is neither increasing nor decreasing at x equal to 0, okay, even though f prime of 0 is positive. Okay, that's the end of this discussion of increasing and decreasing functions. I think this is a very important topic, although it's kind of buried in maximum and minimum, in the discussion of maximum and minimum, and so we don't quite emphasize on these things. But actually these things are more important than finding local max and local min. They are at the heart of those things. Anyway, I hope you enjoyed, and I hope I'll be able to finish the video on extrema relatively soon. Okay, but until then, bye.